will see what are the different types of transfer function representations. Now we know the transfer function definition. Transfer function is a ratio of Laplace transform of output variable to Laplace transform of input variable under zero initial conditions. So we always assume zero initial conditions in transfer function model. Now how can we represent in control systems? Basically there are three ways of representations. The first we can see here, that is called polynomial form of transfer function representation. So it will be like this. Now let us say the transfer function C of s by R of s is equal to, so it is a ratio, we have a numerator polynomial and denominator polynomial. In numerator polynomial I am taking Bm s power m plus Bm minus 1 s power m minus 1 plus dot dot dot, we will get finally B1 s power 1 plus s naught or b naught. So b naught is a quotient of s power 0 divided by, similarly I have an s power n plus an minus 1 s power minus 1. So we can get plus dot 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 up to a naught. So your bm to b naught, an to a naught are the coefficients of both the numerator and denominator polynomial. Now if you look at here, we have s power m in the numerator. That means those many terms you will get when you equate it to 0. Those many roots you will get when you equate it to 0. And we know that the numerator roots are called zeros and denominator roots are called poles. Then what will be the order of zeros? The order of 0 is m. So s power m means there are m number of zeros. Similarly denominator I have n, means there are n number of poles in the particular transfer function. Now depending upon m and n, I can classify the transfer function, again whether it is a polynomial or any other, into three basic. What are they? When this m is less than n, that means number of zeros are less than number of poles, then we call it as a proper transfer function. When m is equal to n, which means the number of zeros equal to number of poles, we call the transfer function as strictly proper transfer function. It is strictly proper transfer function. Now if m is greater than n, which means my number of zeros are greater than number of poles, then it is called improper transfer function. So in linear control system, we are not going to talk about the improper transfer function. Therefore the transfer function will have the number of zeros either is equal to number of poles or less than number of poles. Only we take proper transfer function or strictly proper transfer function. Now the order is n, small n is the order here. We already know the order is nothing but the energy storage element information. If n is equal to 2 means in the particular physical system there are two energy storage elements. It can be either electrical or mechanical, any other physical systems. The second form of transfer function representation is pole zero form. Now here we can represent the transfer function as C of s by R of s is equal to, in the numerator we have k into s plus z1, s plus z2 and so on divided by s power p and into s plus p1 into s plus p2 and so on. So here z1, z2 up to any number of you can have fact. So those are nothing but the zeros, and the p1, p2 and so on, they are the poles of the transfer function. Now we have s power p. So this s power p, the p represents the type of the transfer function. It means if p is 0, it is called type 0 system. So if p is 1, it is a type 1. If p is 2, it is type 2. Means the type of the system is decided by s power p. Now the gain k is called open loop gain. This gain k is called open loop gain. Generally, the pole zero form representation is used to directly look at what are the poles and zeros of the system on S plane. And other advantage with the pole zero form is we can directly draw the root locus of the system. So we know root locus is a very powerful technique for analysis and as well as the design of control system. So to draw the root locus, the open loop transfer function should be in a pole zero form. Now the third one is called time constant form. So in this time constant form we can write C of s by R of s is equal to, so in numerator I have Ks into 1 plus stz1 into 1 plus stz2 divided by, again we have s power p, 1 plus stp1 into 1 plus stp2 and so on. So if you have a transfer function in this form, it is called a time constant form. It is called time constant because so we have a tz1, tz2, tz3 which are the time constant of numerator terms. Similarly tp1, tp2, tp3 and so on called time constant of denominator. So this form is very useful when you draw bode plot and as well as the polar plot. So for frequency response plot generally we go with the time constant form. So what is the numerator gain Ks? So this Ks is called static gain, or it is also called static sensitivity. Sometimes it is also called a DC gain, which means you know the S is a complex frequency. If you make S is equal 0 for all the first order terms, whatever the gain that is available here, that is your DC gain of the system. Now these are the three representations of the transfer function.